So I'm just going to give you a quick overview of hurricanes, aka tropical cyclone. Tropical cyclone is the generic phrase we use for these storms all around the world. A little bit about physics, and then talk about what we know about the relationship between hurricanes and climate, which is a really interesting subject. Well, I think everyone here has probably seen a nice photograph of a hurricane from space. When you look down from space, you see a swirling mass of clouds, 400 or 500 kilometers in diameter. This is a hurricane approaching close to the U.S. There's Florida, for example. When you look down from space, you're seeing the tops of the clouds, which are very close to the tropopause, maybe 15, 16, 17 kilometers above the surface, where the temperatures are well below minus 60 or minus 70 degrees C. It's very cold. Ironically, some of the coldest air you can find anywhere on the planet is in the upper tropical atmosphere. And that would be a point of some significance when we come back and talk about physics this morning. These are cyclonic vortices. They rotate in the same direction as the local projection of the Earth's rotation axis onto the local vertical, which is counterclockwise in the northern hemisphere. The flow is this way. But in the very tops of the storms, the air actually is flowing out and spins the other way, clockwise. So all the clouds you see at the top of the storm are composed of ice crystals, which are below temperatures. The deepest clouds, the heaviest rainfall, and the strongest winds are arranged in an annulus, which you can kind of see there like a donut, called the eye wall. And you'll see in a minute why it's called that. Often surrounding a clear region called the eye, which only typically has clouds in its lower portion and no rain in the winds are fairly calm. Outside of the eye, the thunderstorms, convection is arranged in these sort of spiral arms, which you can see here. Okay. Here is a sort of a closer view. This is from the International Space Station. It's a close-up view of Hurricane Igor of 2010, then a Category 4 storm. And here is the eye. Here is the so-called eye wall. This is the annulus of rapid convection. So air is spinning counterclockwise, but also coming up toward the observer in this case. And then at the top of the storm, turning and going out, eventually in the outer region, the sense of rotation reverses. The eye is a fairly turbulent place. There are all kinds of eddies and so forth in the eye. Here is a photograph taken inside the eye of an Atlantic hurricane. I should add that we have been routinely flying research aircraft into hurricanes since 1945. Actually, the first mission into such a storm was launched from Texas without authorization, I might add, 1943. It's a daredevil flight, but it's done routinely. And it's quite a magnificent sight. A two-dimensional picture can't possibly do it justice. It's like standing in a Coliseum that's 10 miles high and 30 miles across with white walls. Here you see the blue sky, stratosphere. Frequently you see a kind of cascade of ice crystals falling down the inner side of the eye wall. You can see why it's called an eye wall. Literally, it's a wall of clouds. It's underneath this eye wall. And you have the strongest winds and the heaviest rain. These are low clouds, only a few hundred meters above the surface of the ocean. You can see the breaks these clouds there. Well, we've been flying into storms enough that we have a pretty good idea of the structure of a hurricane. This is just sort of a cartoon cutaway, but it's based on actual aircraft measurements. So you're seeing the center of the storm here, kind of a pie slice, 200 kilometers out, 2 kilometers up. And the quantity that's contoured here from aircraft observations is the speed of the horizontal wind. So this orange can be anywhere up to over 70 meters per second in a very strong hurricane. The blue is essentially zero or very light. The strongest winds are, again, under the eye wall. They decay with altitude. And the strongest winds are near the surface in this annulus. That's why they're so destructive. You know, in a good New England winter storm, which we really haven't had one this year, an example of, we probably will, we can also get 70 meter per second winds. But they're 5 or 6 kilometers above the surface, not at the surface, which is why those storms are not nearly as destructive usually as a hurricane. Now, this is a similar cross-section but it's based on a computer simulation, numerical simulation, just integrating basically fluid and chemical equations, as you can imagine, since we do the same sort of thing here. And it shows the vertical component of the velocity, vector velocity. The yellow is being a few meters per second, and the blue being essentially zero, but there's in fact very weak descent in the outer region of the line measured in centimeters per second. And here is the difference between the temperature at any point and the temperature one would normally find at that altitude in the tropics. And so you can see that toward the center of the storm, high up, it's quite a large temperature perturbation. It can be more than 16 degrees centigrade. Not much temperature difference along the surface. So a hurricane is a warm core vortex, particularly at high altitudes. Just a little climatology. This simply shows the tracks of tropical cyclones over the period of 1945 to 2006. Storms that form in the Atlantic typically form anywhere from Africa to the Caribbean and Gulf of Mexico. They travel westward and often curve up to the north and east, affecting the Gulf Coast, the East Coast, even up here in New England occasionally. The Atlantic storms constitute about 12% of the global total tropical cyclones. The rest are in the Pacific and Indian Oceans. In a very active belt off of Mexico, these storms form right off the coast and move westward, very rarely affecting land, which is why you don't hear about them. Occasionally one will make it out of the valley. There's a very active belt here in the western North Pacific affecting the Philippines, Taiwan, the coast of China, Vietnam, up to Korea, and so forth. The Bay of Bengal has some of the worst storms in history in terms of loss of life, and the Arabian, particularly the eastern part of the Arabian Sea. There's another belt in the southern hemisphere from the central South Pacific across the Indian Ocean to Madagascar, Mozambique, etc. Notice that there are no storms within a few degrees latitude of the equator. That's simple. To have a long-lived rotating vortex on a rotating Earth, you need to be able to take the Earth's rotation vector and project it onto what you call up. You get an answer that's not zero. Well, of course, it's zero on the equator. So if you have a retirement project to sail around the world and you're scared of tropical cyclones, just stick to the equator and you'll be fine. Of course, you have other problems there. There's something that physics teaches you that you might find useful.
Why are there no storms between Africa and South America?
Yeah, in South America, in the middle of the Pacific.
It's interesting, yeah, because the proximate answer is because the South Atlantic is relatively cold. North Atlantic is much warmer. There was one storm before you can see it there, like Katarina, which affected Brazil about 10 years ago. Of course, it begs the question, why is the South Atlantic cold compared to the North Atlantic? Ironically, part of the answer to that may be hurricanes themselves. You have a strong ocean current that moves northward through both the North and South Atlantic Oceans, convecting the warmest water into the northern hemisphere. That's another very interesting phenomenon that we could spend easily several seminars on. But there is northward heat transport in both sides of the Atlantic Ocean. As you're probably aware, these are creatures of the late summer and early fall, which is the number of storms per month in the northern hemisphere read off this axis, and in the southern hemisphere read off that axis. So you can see that they prefer the warmer times of the year in each hemisphere. Let's talk a little bit about physics, because at least the energetics of hurricanes are remarkably straightforward, oddly enough, for such an interesting storm. And what we can do is idealize the hurricane as being circular, symmetric, and steady in time. Of course, they aren't exactly either, but they can be remarkably steady and remarkably circular. So we'll think of them that way as a first shot. And here's kind of a cartoon cross-section. So this is the axis of rotation over here on the left, going in altitude from the surface to about 16 kilometers, and then outward about 200 kilometers. This is a cartoon of the eye wall cloud. And if you could attach yourself to a sample of air at A and go for a ride, what you would do is spiral in. Of course, you're rotating rapidly around the axis of rotation. You're also drifting in. until you get to the eye wall, then you go shooting up and out. And then over the course of a few weeks, if you could actually close the system, most hurricanes are open cycle. But you can certainly build numerical models and artificially close the cycle, and you won't get much difference coming down along a trajectory like this. Now the lurid colors on here is it's essentially the specific entropy of a mixture of dry air, water vapor, and condensed phase water, which are all considered to be in thermodynamic equilibrium with each other. So it's sort of the system entropy. And the only way you can change the entropy on the timescales of hurricanes is first by transferring heat from externally from the ocean, and secondly by getting rid of it by infrared radiative transfer. Those are the two sources. So phase change in water does not affect this one. Okay? It's an internal process. One of the things that you will read in textbooks that's quite mistaken and wrong is that hurricanes are driven by latent heat of vaporization when water vapor condenses. That's a similar error to saying that elevators are driven up by counterweights going down. In some funny kind of energetic sense, you could make that true, but it kind of misses the point. You know, we like to think of it as a coupled system of a counterweight and the elevator driven by an electric motor, which in the case of the green building where I work sometimes works and sometimes doesn't. And it's working. That's the way to do it. So let's look at what happens to the system entropy. It starts out low, and as you go in toward the center, it increases. And that reflects essentially the boiler room of the hurricane. This is the heat transfer from the ocean, which in the case of a tropical hurricane largely is a latent heat transfer that happens when water evaporates. Okay? So evaporation of water takes enthalpy out of the ocean, adds it to the air, and that is the process that drives a hurricane. We've known that for 60 years. That's why they die when they go on land. Okay? There's essentially no heat content of the land surface. And then as the air goes up, the eye wall goes up adiabatically, along the line of constant color on this diagram. And then the heat, the enthalpy you got from the ocean is lost up here by infrared radiation in space. And then you have another adiabatic leg. Well, it turns out that these are the four legs of an ideal Carnot heat engine, the most efficient heat engine you can design operating between two fixed temperatures. And remarkably, a hurricane is very, very close to a Carnot cycle. So if you remember what that is, you have isothermal expansion, which is what's happening here. The air moves towards a lower pressure at the center of the hurricane, but is kept at fixed temperature by the contact with the ocean. Adiabatic expansion, and then you have isothermal compression in the lower stratosphere where the temperature is nearly constantly higher, and then another adiabatic compression. Now, you know that the efficiency of a Carnot engine is proportionate to the temperature difference between where you take the heat out when you put it in, putting in about 300 Kelvin, and I remarked before it's very cold at the top of the hurricane, you're taking it out at 200 Kelvin. That gives you a thermodynamic efficiency of about a third, which is pretty good for a natural heat engine. Okay? The one wrinkle on this, which is interesting, is that to a first approximation, the hurricane's doing no work on anything. Okay? It's not exporting any energy, doing a little bit of work to create things like waves on the surface of the ocean. But most of the kinetic energy that's generated by this Carnot cycle is dissipated back into heat in the turbulent boundary layer, especially near point B. So some of the waste heat in this process gets recycled in the Carnot engine. Doesn't violate Carnot's theorem because it's not doing any work at all to start with. It's just increasing the wind speed a little bit.
I was wondering about the equilibrium.
Yeah.
Shouldn't the pressure gradient balance the centrifugal force or something? Must link the pressure to the velocity?
It does, except where you have frictional torque acting on the flow. And that's true in the atmospheric boundary layer. And that means that to counter that, the pressure gradient has to be doing some work on the air. So it must have a component down the pressure gradient. So most of the motion is indeed around the storm. It's not far from gradient balance. But there is this inward drift, which is called Ekman drift. Okay. Here are measurements of the system entropy in a real hurricane. This is a snapshot. This is a quantity called the equivalent potential temperature, whose logarithm is what I call the system entropy. And this is the center of the storm in this case here. And you can see the really elevated heat content or entropy of the air in the core reflects this enormous heat source from the ocean. So that's just a recap of what I said. You have the four legs of the Carnot cycle. And this is the only equation I think I'm going to show in the talk, but you can equate with the mechanical generation of energy in the Carnot cycle to its dissipation and come up with a kind of a neat equation for the largest wind speeds, which we call potential wind speed or potential density, that you can theoretically have in a steady hurricane. And so this is a wind speed squared. This is a ratio of coefficients that govern the exchange of enthalpy between the ocean and the atmosphere and the exchange of momentum between the two fluids. This is the surface temperature. This is the temperature in the outflow at the top of the storm. And then this is the driver. It's the difference between the specific enthalpy of the sea surface and the actual enthalpy of the atmosphere. It's that thermodynamic disequilibrium that drives the hurricane. In fact, humidity of the atmosphere above the ocean isn't 100%, it's more like 80%. So the atmosphere and the ocean are not in thermodynamic equilibrium in the tropics. And something, by the way, that owes its existence to the greenhouse effect prevents the ocean from balancing solar radiation strictly by infrared radiation. You just got to get rid of it some other way to get rid of the evaporative radiation. You get rid of the evaporative potential. Now you might be surprised that this cold temperature appears in the denominator here. It's not what happens in Carnot efficiency, and that is there because of this conversion of mechanical turbulence back into heat under the eyeball, or otherwise at the surface temperature.
Is that what sets the outflow temperature? The kind of mechanical conversion of heat, or is there?
No, it's actually set by where air going over the eyeball becomes neutrally buoyant with respect to its far environment. Nominally, there is tokamak. It's set by the environment. These are subcritical vortices. So internal waves, for example, in the outside vortex can propagate and control the stratification of the outflow. So it's an environmental. You can look at an atmospheric sounding environment and make a pretty good estimate of what that outflow is.
People have talked about setting off an atomic bomb in the eye of existence. Is that just way too small to really affect something 30 miles?
Well, I think unfortunately it would have exactly the wrong effect. Because you have the wrong effect. It would make it more intense. You're taking a
That's what I
more
heard.
persistent.
I don't understand that.
So you have a very intense and very radioactive hurricane.
The washes on the ground are negligible.
Yeah.
Dragging on the ground doesn't do much.
Oh, it does.
You can't get heat. Oh, it does?
Yeah, it
What's
does.
the percentage on that?
Well, it's in the dissipated heating is up to 30% of the total heating under the turbine.
But that's dissipation. It isn't dragging surface and dust and everything, houses and,
Well, it does to some extent.
that's very small.
Okay, this equation looks like it's explicit, but it isn't exactly because these two terms have a pressure dependence. And pressure drops as the storm intensifies, and the density is given by V squared. So there's a little bit more to it than is shown by this equation. If you do it correctly, you graph the solution, you get something that looks like this. This is kind of a partial solution space. This is the outflow temperature. This is the surface temperature. We've assumed that the relative humidity of the area of the surface is 75% in some ratio exchange coefficients. And this is the peak wind speed in meters per second. Now in the real tropics, we live around here somewhere, about 80 meters per second, minus 70 and 30 is about the conditions you see in the tropics. And 80 meters per second is about the largest wind speeds you'll see in mature hurricanes. Remarkably, that equation has a singularity. If you try to go too hot or make the outflow too cold, we call it the hypercane regime. There's a huge phase transition in the character of hurricanes. We simulated it numerically. It's way off the charts. We don't have to worry about this in our climate, but it's a curiosity. And if anyone wants to talk about that later, I'm happy to do that. here is what happens if you graph the annual maximum potential intensity today from climatological data. So this is in meters per second in the deep tropics. You see very large values, Caribbean, Gulf of Mexico, Eastern Pacific, pretty much where you see actual hurricanes. But it's an energy argument. It doesn't know that hurricanes are mechanically impossible at the equator, which I mentioned before. That's why there's numbers right at the equator. Elsewhere, it seems to work. Now, given that as kind of a once-over theoretical background, although it's just energy, really, we're talking about, not mechanics. That would take a long time. It's very, very interesting mechanics. But I can't talk about it. Let's look at what happens with hurricanes and climate. And I'm going to look at a particular metric of hurricanes, which we call the power dissipation index. Now, if you look at the mechanical dissipation of kinetic energy in a turbulent granular, it kind of scales as the cube of the mean wind speed. And so what we're going to do, what we'd like to do is integrate that cube of the wind speed over the surface area of a hurricane, and then over the lifetime of the storm. In practice, we don't have enough data to do the areal integrals. So we can take the maximum wind speed cube and integrate it over the lifetime of the storm and call that power dissipation index, or PDI. So we're going to measure the rate at which storms dissipate kinetic energy. And if we look in the Atlantic, over the last 40 years or so, this is what we see. I'm showing you the Atlantic, even though that's only about 12% of the total, because far and away we have the best hurricane data in the Atlantic. We've systematically been flying airplanes since the mid-1940s, although it wasn't really until the introduction of inertial navigation in the late 1950s that we started to get good wind speeds, and they didn't become really good until about 1970, which is why I'm starting with a series then. Elsewhere in the world, we don't fly airplanes in hurricanes, so even today we're doing a lousy job sampling global hurricanes. We see them with satellites, but satellites aren't terribly good at measuring things that we really need to know about hurricanes, like wind pressure and so forth. So what you see in the Atlantic, these are in units that you don't really need to know about. They're energy units, and they're probably scaled by 10 to the 12 or something, but they're just a linear scale. And you see that it's gone from a value around 0.8 or so, maybe 0.7 in the 70s and 80s. It's increased to a larger value in recent times. Well, that, who knows why, but there it is. These are pretty good measurements. We believe the measurements. There's variability in all sorts of time scales. We've smoothed this, though, with a filter to take out the strictly year-to-year fluctuations, which can be large. Now, remarkably, if we plot on the same graph the sea surface temperature, or SST, of the part of the tropical Atlantic where hurricanes typically form during hurricane season, you get the blue curve. And it's highly correlated with the red curve. That's pretty well known. And it's somewhat predicted from the Carnot cycle theory that sea surface temperature really isn't the driver, but it's a pretty strong cofactor in what's really driving the system. And so you see this nice correlation, including this sort of 11-year cycle that you kind of see here, and then the trend that you see towards the end of the second half of the series. Now, we thought, well, that's interesting. We didn't expect to see such a good correlation. Our hurricane records going back to the early part of the century aren't very good, but there are records. On the other hand, our records of sea surface temperature are very good, going back all the way to the 19th century. It's been a lot of work on that. So let's just use the linear regression relationship between these two curves, and then take the sea surface temperature and make a backward prediction of what hurricane power would have been like in the Atlantic. And then you get this, going all the way back to the late 19th century. So you see this sort of quasi-11-year cycle in sea surface temperature. You see this longer pattern where you have a big rise in the mid-century, a decline from the mid-century to the 70s and 80s, and then a pretty big rise toward the end of the century and into the beginning of ours.
What's the origin of the 11-year cycle?
Well, we thought when we looked at this as a dead cinch we're seeing the solar cycle.
Yes.
And I put a student to work on it immediately, and he came back and said it's not coherent. and it turns out not to be. So we don't know. The only answer, sensible answer to your question, unfortunately, we don't have any idea. But it's really there, both in the SST and in the hurricane data, which of course are completely independent measurements. Now, the remarkable thing is, I mentioned to you that we do have records of hurricanes that nobody thinks are very good at the beginning of the century. And we could just take that hindpass and compare it to the records that exist in the historical database. And that's what you get. That's the red. That's the actual taking hurricane power from the hurricane database. And even though we don't think much of it much before 1960, it lines up nevertheless pretty well with sea surface temperature from back then, except from about 1939 here to about 1945, it's a huge anomaly. So I'll let you chew on that. We can start to speculate, and we can talk about it later if you like. Yes.
Isn't the heating of the planet maybe due to the 1.6 billion gas-powered automobiles on the planet? Fogging? I notice when I fly across the country, every time I go, it seems to be foggier and foggier going across Nevada or California.
Yeah.
That's definitely noticeable.
Well, we'll come back. We're actually going to come back and talk about what we think we know about the seesaw. So what we discovered looking at the data is this power dissipation has more than doubled since the 80s. Even though the sea surface temperature's only gone up a half a degree, that's a little bit of a mystery why that should be so sensitive. What's causing the Atlantic sea surface temperature change is a natural question to ask, the question you asked, what's doing that? Well, we think we know. Let's skip over this 11-year cycle, which is a very interesting question, and look at the longer period variability. So what I'm showing you here is the August through October sea surface temperature in the cyclone producing regions in blue. It has just been smooth with a 10-year running average, that's all. We emphasize the longer period variability. Again, you see a decline in the early part of the century, a rapid rise in the mid-century, another decline, and another even more rapid rise. I've taken out the long-term mean, so I've centered it at 0 degrees C. And then I've done the same thing with the whole northern hemisphere surface temperature. That's including land. It's the whole hemisphere, of which the tropical Atlantic is really a very tiny piece. And you can see that on this time scale, they're basically doing the same thing. Tropical Atlantic summer isn't doing anything differently from the northern hemisphere. So we can ask maybe a simpler question: why did the northern hemisphere do that number? And there's been a lot of work by colleagues of mine all over the world trying to attribute climate change to the 20th century. And there are all kinds of studies, and I'll just show you one. This black curve is now looking at the global, not the hemisphere, but the global mean surface temperature.